Now, there's been an interesting sort of change in our understanding of different forms of phosphorus and what's important and what's not important. I would say over, well, probably my lifetime, over the past 40 years or so. And originally, the idea is that, phosphorus doesn't move from land. It likes to hold on to soil. I call it sticky when I talk about it usually. And therefore, what the bulk of the phosphorus that gets into a river and ultimately ends up down in a receiving water body like Lake Erie is in a particulate form. It's associated with particles. And so you see muddy water and there's a lot of phosphorus there and you have to be worried about it. So a lot of the early efforts to deal with phosphorus all had to do with, well, if we control soil erosion, we control phosphorus because phosphorus is just particles. And that's not wrong. Like nothing about that is necessarily wrong because still the bulk amount of phosphorus is associated with those particles. But what we've been learning over time, especially with more recent algal blooms in Lake Erie, is that it seems like the smaller portion of phosphorus, the dissolved phosphorus that you can't see, is actually way more bioavailable for algae. It's way easier to use. And if we're thinking of it in an agricultural context, I think of dissolved phosphorus as like the crop available phosphorus, right? They're not entirely all that different from each other. And so when we look at what we've seen most recently in Lake Erie, we've seen this increase in dissolved phosphorus that in the late 90s that make it to the lake. And then that came with a whole new resurgent of blooms.
Laura Johnson and her colleagues at the National Center for Water Quality Research at Heidelberg University, along with scientists at EPA and other labs, have determined that 88% of the phosphorus in Lake Erie comes from non-point sources. Those sources include farms. That's a big change from a generation or so ago.
The big hole in the story is, why did dissolved phosphorus increase in the first place? If we know that, then we can fix it, right? That's really simple. And I would say that there's a list of things that changed between the mid 90s to the 2000s. I would say maybe even late 80s through the 90s to the 2000s in agriculture is extraordinarily long, right? Farms got larger. There was fewer farms, right? Equipment got larger, so there's more soil compaction. We saw the introduction of GMO crops that can then allow us to use Roundup at different times to control weeds. That helped with the conservation tillage movement, so then we don't have to till the ground any longer. But in doing that, combined with how phosphorus is typically applied, that's allowed for potentially more accumulation of phosphorus on the surface. In addition, we also know that part of the conservation tillage movement is to have high residue, which is good for soil. We need to have better organic soil so that we can have better yields. But then again, that residue also has phosphorus in it. And so what we think here, there could have been any of those things can be, a cause. But what we think here and what we've done some measurements of is looking at where phosphorus is located in the soil column. When you take your soil test level, is it all up in the top 2 inches or is it well dispersed throughout the whole soil column? What we found is that most of the phosphorus in some fields was actually in that top 1 to 2 inches, which is the worst case scenario for dissolved phosphorus loss, because that's what interacts the most with rainwater. However, if you were any farmer in this area, you'd be like, but who cares about the surface? All of our water goes through tile drains, don't you know? And tile drains filter everything through the soil column before it gets into the subsurface drain, and then it runs off into a ditch. But our heavy clay soils up here in the Western Lake Erie Basin lead to these cracks and fissures in the soil, root channels, earthworm holes, basically these highways. We call it preferential flow and macropores, but basically highways between the surface and the subsurface, so that now highly concentrated surface water has a way to get into tile drains and then out into the streams and ditches.
The pathways in the soil and the solutions to the challenges can be different in different fields. The challenge, says Hans Koch of the Conservation Technology Information Center, is that it only takes a little phosphorus to create a big problem in watersheds like the Western Lake Erie Basin.
So there's a very small amount of that phosphorus that runs off. However, the issue is that a plant needs a fair amount of phosphorus, like in pounds, while the algae in the lake only need tens or hundreds of pounds of phosphorus to be very happy. So even if a farmer only loses 2 to 5% of the phosphorus from their fields, that still means that is too much for the lake. And you still get algae blooms, especially with the increased spring rains we've been experiencing. And the phosphorus component that is really causes the most damage is the dissolved reactive phosphorus, which is only a percentage of the total phosphorus runoff. But that is what causes the algae blooms, and especially the timing when it goes into the watershed is very detrimental to the size of those algae blooms.
Reducing phosphorus in the western Lake Erie Basin is complicated, but independent crop consultant Greg Kniebuehler says a good place to start is the 4 R's of nutrient stewardship and the technology to implement them.
And so there definitely is a problem. I mean, phosphorus is a problem. I'll admit it. Farmers will admit it. But technology today, like variable rate technology, low and spread out application rates, timing of application, just being smart about things can totally change what water actually ends up in that watershed. And I've always contended that there should be a 5th R, and that 5th R should be data. So you have the 4 R's, a right rate, right source, right timing, right placement. There should be a 5th R, and that's data, because you can't make any of those decisions without the data to confirm or disfirm the decision to be made. And so that's one thing that we do by, as a starting point anyway, just mere soil samples to back up the data decision made to determine is phosphorus even needed, and should a phosphorus application go on.
Les Seiler farms in the western Lake Erie Basin. He's a 30-year no-tiller. About 10 years ago, he and his brother Jerry added cover crops because they improved soil health on the farm. The advantages in terms of phosphorus turned out to be a big bonus.
I'm Les Seiler. We're in Northwest Ohio, Fulton County. I farm with my brother. We farm just about 1,700 acres, corn, soybeans, wheat, malt barley, alfalfa is our crops. And we've been incorporating cover crops for 10 years. And we was long-term no-till for, we've got farms that have been no-tilled for 35 years. So we started this whole thing because we had erosion problems and found the no-till to be a real fix for that, or a help. It was a helpful tool. And we didn't see any improvement in the soils as far as soil health. So we started learning more about cover crops and incorporating them into the farms, and we started seeing improvements from a soil health perspective, organic matter, additional water holding capacity. Things just seemed to work a lot better. And a lot of our soils were heavier clay soils. So I mean, the benefit of the no-till was, you could see things was better by doing it.
Adding crop diversity, including wheat, provided the next big boost.
Corn and beans. Corn is a high residue crop. It will increase your organic matter because it's higher in residue. Soybeans are kind of a minor. They pull it down. So if you're just corn and beans and you've got a 2% organic matter, you're probably not going to ever change that. I've seen it where corn will build it up maybe 0.4% and beans will mine that off. So you're never going to see an improvement. But then you throw wheat in, which is another high residue crop. And we do not bale straw. We try to return everything.
As they build their soils, the Seilers are doing more than just increasing organic matter. They're tapping into nutrients that are already there, to the point that they no longer apply phosphorus before corn.
The biggest reason we quit using phosphorus is because I knew we had numbers that were high enough, and I had the confidence it's time to not worry about phosphorus being the limiting factor. And we started to focus on some other stuff. We focus on zinc, we focus on boron, we focus on calcium. And I think there's some things there that are have been a lot more beneficial to us. And the fact that you can't have calcium and phosphorus together because they'll solidify, it was just a good reason to eliminate the phosphorus part of it. And I can always put it in a corn crop if I need it through other ways. But what I've seen with these other nutrients that we've been putting down with our pop-up and stuff, we've been raising better corn. I mean, it's all about getting that plant off to a healthier start, and the nutrients that are in the soil from the breakdown of the previous crop residue seem to have a lot more value in uptake for the plant than the commercial stuff that we can put out there.
In addition to the management the silers do in the field, they also have a two-stage ditch, which reduces erosion and captures soil particles and phosphorus.
What we had here is a farm where this ditch was a very windy ditch and ran very fast during the high events, and the speed was very destructive on the curves and stuff, and it was just eating away at the banks. I mean, just very destructive because of the speed. So in 2014, with the help of the Nature Conservancy and local soil and water and many others, we got to put in this two-stage ditch on this farm. And the benches, I think, are supposed to be about 35 foot. The banks are about 2.5 to 1 slope. And what we've seen here is it gave it the ability during the larger events to slow the water down and make it a lot less destructive, and keeping a lot more soil in place. So instead of this soil all leaving here and going down to the Lake Erie and adding to all the sediment they're dredging out, we can hold more into this stream bank and hopefully handle those events a lot easier.
The way the vegetated banks slow down the water helps capture phosphorus, says Koch at CTIC.
Some sediment might fall out in those places, but also the water is in contact for much longer with the vegetation, which gives it a chance to lose some of the phosphorus to the vegetation. And those things have been studied widely over the whole Midwest, actually, not just in the Western Lake Erie Basin, and they're very effective in doing the erosion control and the phosphorus removal from runoff water.
On most farms, the challenges with two-stage ditches are the amount of land that must be taken out of production, the cost of moving soil, and the expense of maintaining vegetation. Hans Koch describes another engineered approach, also expensive, but also effective on dissolved reactive phosphorus.
A more engineered approach is the use of bioreactors. And bioreactors have been around for quite a while, mainly for the undoing of nitrogen coming in drainage water, nitrogen from fertilizers. And for nitrogen, we use basically big tanks or basements on the edge of a field that are filled with wood chips. The drainage water runs through there, and the nitrogen gets tied up on the carbon that is in the wood chips. And then once that is all deteriorated, you replace your wood chips and you can use it again. Now, for phosphorus, wood chips are not very efficient. So we use things like slag out of the steel industry, and that takes up a lot of phosphorus in the slag. But both systems are very expensive. We come up with values around $100 per pound of phosphorus that is taken out by these systems. And you compare that to the cost of the actual damage the phosphorus is doing to the economy in the lake, which is over $1,000 per pound of phosphorus ending up in the actual lake and impacting our fisheries and tourism. The $100 is probably a good approach if we can keep it on the farm fields for that $100 per pound of the dissolved reactive phosphorus, and we do not have to construct all the bioreactors and or two-stage ditches. That is probably a good start on a phosphorus economy to see whether that's affordable.
That $100 per pound figure is important. It's the starting point for a pilot program to create a market for phosphorus credits, paying farmers in the Western Lake Erie Basin to reduce the amount of phosphorus that escapes into the waterways.
Farmers would get paid by the pound of phosphorus they prevent from going in the lake. So it is somewhat similar what we saw with the Clean Air Act, where people were very interested in keeping sulfur out of the air. And you can either do that by putting very expensive mechanisms in your power plant, for instance, to catch the sulfur, or you can do it by preventing other sulfur sources to go into the air. And like they did with purchasing a lot of old vehicles. We are doing it straight by having the farmers prevent the phosphorus from going into the lake by implementing best management practices and getting rewarded for do that. But we measure it in pounds of phosphorus, and we use computer models and satellite imagery to verify that that is actually happening, that the phosphorus is actually being kept out of the watershed, and then we pay the farmers for doing that.
For the Western Lake Erie Basin Pilot Project, Bayer stepped up to be the buyer of phosphorus credits. Organizers of ecosystem services markets like phosphorus credits rely on models to estimate the impacts of the practices they encourage. At Heidelberg University, data analyst Judy Smith describes a key tool being used in many parts of the country, including the Western Lake Erie Basin Project.
NTT stands for the Nutrient Tracking Tool, and it was actually developed by Tarleton State University in Texas. It runs off of the APEX model, which is the agricultural policies / extender model. APEX is known to be very useful for modelers, but NTT was really built for the end user. So farmers and crop consultants, those kind of people who might want to use a model but don't have the expertise. And so NTT is a field scale agricultural model that uses inputs such as weather, soil, the farm shape file, crop rotation and management, all that kind of data that a farmer would have access to. And then it outputs things like crop yields, water yields, and even what we're really interested in is nitrogen and phosphorus runoff.
When it all comes down to it, reducing phosphorus loads in watersheds like the Western Lake Erie Basin isn't just a good idea. It's got to happen. And for farmers like Les Seiler, incentive programs are helpful to make it happen. But ultimately, for Seiler, reducing nutrient loss is as much about becoming a better farmer as it is meeting society's demands to help improve water quality. He points out that only about 1/3 of the 1034O that gets applied to farmland finds its way into the crop. That's not enough, and it's time for that to change.
I mean, look at it this way. If your car was running at 30%, would you keep running it? I mean, if your tractor, anything, would you continue to keep operating that way? And one old guy told me yesterday, he says, you know, a lot of these guys that won't never change, they've changed tractors and planters how many times in the last 50 years, but yet they won't change that fertility. They won't think about that. If you do what you've always done, you'll get what you always got.
We'd like to thank our generous sponsors for making it possible to bring this virtual tour to you today. CTIC is a member organization, and our members, sponsors, and partners are the key to our success in so many ways. To view this video again, see bonus online content, or find much more information about all kinds of conservation farming systems, visit our website at ctic.org.